All right, so the primary topic for this chapter is solutions. Now, in terms of what we're covering out of this chapter and what we're not covering, we're basically just looking at the meat in the middle. So the first couple of sections of the chapter, maybe the first 3 or 4, are largely review materials of stuff that we've already talked about. And I'm going to give us just a couple of snapshots here, just to kind of review and retrain us for that. And the stuff at the end is stuff that we're not going to talk about at all. Stuff that's irrelevant to our course and to what we're trying to do in this course. So if you notice that we aren't reading some of the chapter sections, that's why. So our main focus is on calculations for this chapter. Now, before we get to those, let's just do a little bit of review of some of the terminology and some of the concepts that we have seen before when discussing solutions and aqueous solutions. So just as a review, a solution is a homogeneous mixture. So go back all the way to the beginning of our class here. We talked about the ideas of mixtures, physical combinations of different substances. And a homogeneous mixture being one that had a uniform appearance. I couldn't tell one component apart from any of the other components. That's what a solution is. Now, inside of that solution, we have the solvent. The solvent is the thing that is present in the greatest amount. And then we have solutes, things that are dissolved in the solvent. And a solution can have as few as 1 solutes or as many as, well, practically infinite. Ordinarily, we usually think about solutes in terms of there's maybe 1 or 2 in a given solution, at least one that we might study further. We get into more consumer products like soft drinks, Gatorade, those kinds of things. We're going to find that the solution is water and an ingredient list of 20, 25 other things. Still counts as a homogeneous solution because, again, it has a uniform appearance. I can't tell any one of those components from the others, but I could separate them from each other physically if I needed to. We get solutions from the combination of substances that have similar polarities. The general principle here is like dissolves like. What we mean by that is polar substances dissolve in other polar substances. Water is a polar substance. It dissolves other things that have similar polarities. So things like sugar, things like salts, things like other polar solvents like alcohol. When we have dissimilar polarities, we tend not to see mixing. So if I take something non-polar like oil and try to mix it up with water, it doesn't work. The water's polarity versus the non-polar nature of the oil mean that they're not going to interact very well with each other. The water basically will squeeze out any oil molecules that happen to get in between them, and they separate and form layers. So that's our first set of review concepts. As you saw in lab this week, one of the ways that we can quantify solutions is based on its solubility. And there are 3 ways of quantifying solubility from kind of a broad perspective. Now, the term solubility generally refers to how much of a given solute can I cram into a certain amount of of solvents. Usually the benchmark is 100 grams. If I have 100 grams of water, how much sodium chloride can I get to dissolve in that 100 grams? That would be considered the solubility limit of sodium chloride in that water. And so when we talk about solubility limits, there are three different terms that can get used. If we are at the numerical solubility limit, we call that a saturated solution. And we can usually tell a saturated solution from others because when I go to try to dissolve more solid in that solution, I can't do it. So if I'm at the solubility limit of salt in water, I know I'm there because if I try to pour more salt in there and get it to dissolve, it doesn't dissolve. At any point before the saturation limit, the solution is said to be unsaturated. And so an easy way to tell that you have an unsaturated solution is you go to add more of that solute to it and it dissolves. So if I have water sitting on the table and I add salt to it and the salt dissolves, I know that I have an unsaturated solution. And basically I know that it's unsaturated until I add salt to the water and it no longer dissolves. That's when we know we've hit the saturation point. So am I correct? This was one of the things that was in lab. Okay. And so you saw an example of supersaturation in the lab as well, right? Where you think it's probably sodium thiosulfate or something along those lines. You have a solution of it that's already saturated. You added a whole bunch of the thiosulfate to it, heated it up to get it to dissolve. And then as it cooled down, the salt did not come out, stayed dissolved, at least temporarily. So supersaturation is a phenomenon where we have a solution that is technically above the solubility limit and yet has not crashed out, has not separated into that undissolved piece and that dissolved piece. Now, the thing about supersaturated solutions is that they're usually unstable. And as you saw in the lab, any small bit of disturbance inside of that test tube is enough to cause that solid to start to form inside of the test tube itself. And so it'll give you simple things, just a matter of bumping the solution or even scratching on the inside of that test tube and creating a surface for the solid to form. Or probably what you saw, I wasn't there in lab with you, but taking just a small crystal of that solid or even a piece of dust and dropping it into the solution is enough to cause that solid to crash out of the solution, and you end up getting a whole big mess of solid separated from the rest of the solution. So those are all related to solubility limit concepts. So again, the way to tell the difference between each of them would be, from a physical standpoint, what happens when I try to add more. In the case of an unsaturated solution, the extra dissolves. In the case of a saturated solution, the extra doesn't dissolve. In the case of a supersaturated solution, not only does the excess not dissolve, more solid comes out of the solution with it. And so we end up with more solid in the bottom than what we put in addition. Now, the other thing that you saw in lab, and I regret not preparing you for this a little bit better because we took some extra time to go through stoichiometry and some of those other concepts. It would have been helpful to have had this particular lesson Monday before you did the lab rather than kind of reviewing on it now. And I realized that kind of late. It was sometime late Monday evening. I went, oh, I misread the lab schedule. I thought you were doing that lab next week instead of that day. So yeah, I regret the error there. For those of you that really struggled your way through that lab, I do apologize. I hope that your lab instructor was able to kind of help drag you through it a little bit. Hopefully after today, a lot of those calculations that you had to do then make a little bit more sense. And so when you go into the quiz situation that you're about to go into, you should feel a little bit more confident about it. So when it comes to concentration, this is another way of quantifying solubility, but doing so more with numbers rather than with descriptions. And for our purposes, there are two different kinds of concentration units. There's mass percent, and then there's molarity. Now, in both cases, what we are really focusing on is the relationship between the amount of solute, so the amount of stuff that we're trying to dissolve, and the amount of total solution. And the key word there is solution, not solvent. So let's take a look at each of these individually. So starting with mass percent. Mass percent is simply the ratio of the mass of our solvent, or excuse me, the mass of our solute, the thing that we're trying to dissolve, divided by the mass of the total solution. Since percent literally means per 100, we take that ratio and we multiply it by a 100 to get the percentage. What that also tells us is if we have the actual value for the mass percent, it tells us how many grams of that solute fit in 100 grams of the solution. And so I can literally take that ratio and use it to figure out how much I need of a given thing. So if I have a solution that is 5% sugar, what that means is that I need to measure out 5 grams of sugar, 95 grams of water, put them together. That gives me my 100 total grams of solution. Now, just as an interesting side note, you might have heard concentration units parts per million or parts per billion before. They're especially used for like environmental study samples when you're trying to track toxic materials through groundwater or in different kinds of consumer materials. The only difference between percentage and parts per million and parts per billion is the number that you multiply by at the end. So percent, parts per 100, you multiply by 100. Parts per million, you'd multiply by 1,000,000. Parts per billion, you'd multiply by 1,000,000,000. But you would still use this very same ratio to figure out the relationship between the solute and the total solution. It just becomes a matter of what is your context. Am I talking about mass per 100 grams or mass per 1,000,000 grams or mass per 1,000,000,000 grams? That's really the only difference between them. And so in this course, we won't deal with parts per million or parts per billion. I'm merely providing this to you because it's something you might have seen or heard before. And I just wanted you to know that it's really not different from what we're talking about here. Now, as I kind of alluded to, because mass percent is a ratio per 100 grams of solution, we can use the percentage values to give us some of that context and use that to convert from one thing to another. So if I were trying to figure out how many grams of a certain material to measure out to make 50 grams of solution at this particular concentration, I could put the percent in as grams of solute, 100 grams of solution as the denominator, and use that as a conversion factor to calculate between grams of solute versus grams of solution. That can be really useful for what if I'm creating a solution that isn't 100 grams? What if I'm creating a solution that's only 25 grams? How much solute do I need to measure out? How much solvent do I need to measure out to get to that 25 grams? So let's take a look at some example problems involving mass percent, just to give us some practice here. So I have two practice problems. First one, we've got a soft drink that has 42 grams of sugar and 311 grams of water. What is the mass percent of sugar in this soft drink? Well, if I follow my equation, the percentage is mass of solute over mass of solution times 100. My solute is the 42 grams of sugar. My solution would not just be the 311 grams of water. Remember, solution is all of it. So it would be the mass of the sugar plus the mass of the water. So 42 plus 311 is 353. So 42 grams divided by 353 grams times 100. 42 divided by 353 times 100 to 2 digits, because I only have 2 here, would be 12%. Any questions so far? All right, same kind of question here for the second one. I got 132 grams of potassium chloride and 598 grams of water. So my solute is the 132 grams of potassium chloride. My solution would be the 132 grams of KCl plus the 598 grams of water. 132 plus 598 is 730 grams of solution times 100. So 132 divided by 730 multiplied by 100 to 3 digits this time, because I've got 3 in the numerator and 3 in the denominator. It would be 18.1%. So this would be an example of a direct calculation between what our data are and the mass percent. And so the key to getting these kinds of problems correct is just to make sure that you know what goes where and that you're calculating the solution mass correctly. So sometimes they'll trip you up and tell you the mass of the solution instead of the mass of the water. And if that's the case, you don't do the addition, because the mass of the solution is what's supposed to go in that denominator. But in the case, both of these cases, they were giving us the mass of the solvent. So I need to put the solvent together with the solute to give us the total mass of the solution. Right. Any questions with either of these two example problems? All right, before I let you try on your own here, let's look at an example conversion question. So in this particular question, we are told that a sample of lake water is 8.5% carbon dioxide by mass. The question is, how much carbon dioxide would be in 28.6 grams of water? Now, to answer this question, we have to break down what the percentage means. And so what that percentage means is that I have 8.5 grams of carbon dioxide for every 100 grams of solution. So this is my conversion factor. This is the thing I can use to convert grams of water into grams of carbon dioxide, or grams of carbon dioxide into grams of solution. Now, in this case, I have 28.6 grams of solution. And so I'm going to need to use this conversion to cancel out the grams of solution. And so it's 8.5 grams of carbon dioxide for 100 grams of solution. My grams of solution cancel. My answer, 28.6 multiplied by 8.5 divided by 100 to 2 digits. Since my percentage only had 2 digits, it would be 2.4 grams of carbon dioxide. So that would be one way to solve this problem. Now, another way that you could go about this is, since we have the equation for percentage, you could set up an equation and solve for X using algebra. The reason I wouldn't go this particular direction is because there are too many moving parts. To solve the algebra, I need to divide by 100 and multiply by 28.6 to get X by itself. And raise your hand if you like algebra enough that you want to make sure that you're moving all the pieces in the right direction. Yeah, that's kind of what I thought too. So while algebra is an option, and we could use the equation to get the same place, I find that the dimensional analysis is a lot easier to follow because we don't have to worry about what do I do? Do I multiply or do I divide? And especially if we have that X in the denominator there, that makes it even more complex because we got to remember to bring the X out of the denominator before we try to solve anything. All right, chance for you to do some work here. You've got one question of each type. First, figure out the mass percent of sodium chloride in this solution. Second, figure out how much solution you need to get the 12 grams of sucrose. I'll give you a couple minutes, try to scratch something out on your own here, and then we'll go through the answers and we'll talk about molarity. Okay, walking around, most of you are on the right track with the first one. Pretty straightforward application. I just need to take 7.55 grams of sodium chloride, add together the two things in the bottom to give me 4.64% as my mass percent for that first one. If your numbers were slightly different, 4.65, 4.63, it's probably a rounding thing more than anything else, but you're definitely on the right track. Now, for the second one, what you needed to do was you needed to turn that percentage into a fraction. And so the fraction that you needed was 4.1 grams of sucrose for every 100 grams of solution. Now, for this example, I turned it around on you. Instead of giving you grams of solution to turn into solute, I gave you grams of solute to turn into solution. So what you have to do, you have to flip around the fraction as well. Make sure that the grams of sucrose were canceling out to give you the grams of solution, because that's what the question was ultimately asking. So the answer there would have been 290 grams of solution in total, because the goal was 12 grams of sucrose, not 12 grams of solution. So to get the 12 grams of sucrose, I had to have 290 grams of solution in total. Right. Questions with either of these two? Okay, so the other concentration unit of note for us here is molarity. Now, molarity is very similar to mass percent in that we're looking at the amount of solute compared to the amount of solution. The main difference is what the units are. In mass percent, it was grams of solute and grams of solution. In molarity, it's moles of solute and liters of solution. And so what this changes about the dynamic here is that we can't simply just use a balance to make these kinds of solutions. We usually have to use a volumetric flask of some kind. So if you remember from that lab, you had to make those solutions in 100 milliliter volumetric flasks or 50s or something like that. And those have that one mark on them that measures exactly that particular volume. Now, for our purposes, in terms of calculations, there are really two different calculations that we can go to for molarity. One of them is just turning starting materials into molarities. So I have grams of substance and I have milliliters or liters of solution. What's the concentration? The other is the reverse. I take the molarity and I figure out how many grams I need to measure out. So for that first kind of example, it's going to look something like this. Calculate the molarity of a solution made by putting 15.5 grams of sodium chloride in the beaker and adding water to make 1.50 liters of solution. For molarity problems, it's really important to just remember what we're striving for. So we want moles of sodium chloride divided by liters of solution. Now we already have the liters of solution. That part was given to us in the problem. What we don't have are moles. What we have instead are grams. And so what we need to turn to is a familiar calculation, turning grams into moles. So how do we go about doing that? Well, we've got to go back to our old friend, the periodic table, and we've got to calculate a molar mass. Sodium is 22.99. Fluorine is 35.45. Together, 58.44 grams for every mole. Grams cancel. 15.5 divided by 58.44. The three significant figures is 0.265 moles. So our molarity is the 0.265 moles of sodium chloride divided by the 1.50 liters of solution. 0.265 divided by 1.50. Again, the three significant figures will give us 0.177 molar sodium chloride. Just some things to be on the lookout for, easy ways to get tripped up on these kinds of problems. It's not uncommon to see milliliters instead of liters in terms of describing the solution. The only thing that you have to remind yourself to do is to convert those milliliters into liters by dividing by 1,000 first. And usually that'll be something that kind of makes sense to you, because if you forget to do that, more often than not, you're going to end up with concentrations that are really, really small. So instead of 0.177 like this one, 0.000177 instead, where everything seems to just be really small. And most of the time, our concentrations are somewhere between, like 0.1 or 0.01 and like 10 at the most. All right, questions with this example problem? All right, let's take a look at the other kind of problem. What if I have to figure out how to make a particular solution? Kind of what you had to do in lab earlier this week. How do I make a 0.2 molar solution of iron chloride or something like that? So regardless, the question is, how do I go about doing that? Now, the process here is that we have to understand that molarity is moles over liters. And so if I take that molarity times liters of solution, that will give me moles of solute that I can then turn to grams using molar mass. So this is kind of the scheme that we would use to solve a question like this. Take the molarity times the volume to give me moles, convert the moles into grams using the molar mass. Now, the tough part about this one is that we're dealing with sucrose. Sucrose has a gigantic molar mass. It's going to take more than a second to calculate. So, but let's start with the first conversion. I've got 1.72 liters of solution. I'm going to multiply that. 1 liter of solution is 0.758 moles of sucrose. So my liters of solution cancel. And then 1 mole of sucrose as a molar mass. 12.01 for carbon times 12. 1.01 for hydrogen times 22. 16 for oxygen times 11. For a grand total of 342.34 grams. So my moles of sucrose cancel. I'm left with the grams. I do the calculation, 1.72 multiplied by 0.758 multiplied by 342.34. The 3 significant digits, we get 446 grams of sucrose. So again, if you're asked to make a solution of a particular kind, a particular concentration and amount, take that concentration and that amount, multiply them together to give you the moles, then convert the moles into the grams using molar mass. So really, the only thing that is kind of different here is just how I'm getting the moles from the solution data. All right, questions with this example? All right, in the interest of time, We're not gonna be able to get both of these questions done in the next 2 minutes. For the sake of your vote, of your participation point, let's look at this first one just because it's relatively simple. This is another variant of the first kind of question. Remember, molarity is moles of the solute over liters of solution. Since we're already given the moles of solute, the 0.127, the only thing left for us to do is that is 655 milliliters. We need to turn it into liters before we can use it. To turn it into liters, remember we divide by 1,000. So it's 0.655 liters, which means that the molarity is 0.127 divided by 0.655, which would be 0.194 molar solution. So go ahead and put the 0.194 molar in and get that extra participation point for today. On the annotated version of the slide, I will answer this question there for you as well, help you with the homework. This should get you through the homework itself, though. On Monday, we will talk about two concepts, dilution and stoichiometry. But like I said, we're going to cheat around stoichiometry using something called the titration equation, which will help you out a lot with that lab that you're going to do next week. With that in play, have a great Easter weekend. I'll see you on Monday. Good work today.